dx? Put the dx here.
Mm-hmm.
Josephine, step 3. What do I do? Yep, I'm gonna divide by 1/5 du. I wanna do this so I know I can get rid of all x's. No variables came up, so I just got this dx. Which things do I substitute? All right, I'm gonna keep doing this till you get tired of me going in here and going what? Woo, bye-bye. What's that become?
U, sine of u.
That's a u. The sin stays though, right?
Mm-hmm.
The sin stays. What replaces the dx? That third place has a box. See, that box. What's this coming in and doing what here?
1/5 du.
You're gone. 1/5 du. That looks sloppy. Where do I put the 1/5?
In the front.
Man, you're good. Sine of u. Du. See, I'm happy. Do you see any x's left over? If I had an x left over, I'd be in trouble. That means I didn't do this properly, or it's not possible to do substitution rule. Sometimes it's just not possible to do it.
Now you can get
Like
rid of
e to the x
the,
squared.
get rid of the s.
Yep, now let's go over here. SC. Which way are we going? That way, derivative or anti?
Anti.
And I put the negatives on which one?
Third and the fourth.
Third and the fourth. Right, Amber? We're doing antiderivative, so what's the antiderivative of a positive sign?
Negative cosine.
Negative cosine. Right?
Yeah.
All right, so negative 1/5. Put it in front of that 1/5. Sine of u. This is this a definite or indefinite integral?
Indef.
So let me change my directions. That's an indefinite integral. Evaluate the indefinite integral.
What happened to the 5?
Oh, you're the best. I meant to do that.
She got you, Joseph.
Thanks, Josephine. Hey, do I have to put a plus anything?
Plus c.
Plus C, oh, don't forget because it's indefinite. Now look over, you're about to turn in your test next Monday, you're about to turn it in. Look at that curve, did you forget anything? You. Yes, yes, good job.
5x.
Resubstitute. This was an indefinite integral, so cosine of. So Salmon, outstanding. He's
But
like,
you
hey,
don't need
don't
the
forget that.
c, right?
We
You
need
do need the c.
indefinite integral. Plus constant, it's the
When
antiderivative.
do you need the c and when do you not need the c?
Plus C when it's indefinite, you need the plus C.
Indefinite.
Yep, right down. She's gonna go, I need to put plus C when it's an indefinite integral.
You see when when you see that s thing, with the two numbers up, top and bottom, you don't need the c.
Don't need it.
Oh, when you had the 2 numbers on the top and bottom, then
Yeah.
you don't need the c.
C.
Yes. You got it. Hey, how can I check that?
You can take the derivative.
Love it. So if you ever wanted to check any of these, take the derivative. You gotta do chain rule. Let's go back to that. This is the opposite of chain rule, right? Cool. Alright, let's try another one. I like to build this slowly, if you don't mind. Slowly, because you rock and roll, you hit anything. If I start throwing exponents like x squareds and x cubes, I think you're gonna notice what's gonna be the power difference.
1.
1. So check this out. Okay, I'll use cosine. Well, then that's how I'd have to set it up. I know. Oh, wow. X to the 4th and x cubed, huh? X cubed and x to the 4th. No, we'll be good. But Josephine, I do want to point out, when I set this up, did you notice my power difference? X to the 4th, and this over here is what? X cubed. You'll see why. Because guess what you're letting u equal to? The one that's higher by 1. Oh, the thing in the parentheses. All right, step 2, differentiate. Now, what is the derivative of x to the 4th? 4x cubed dx. Josephine, step 1. Step 2, right? Good. Step 3, I always divide out the what?
The
The number.
Constant.
Yeah, divide out the number. very good. I'm gonna just divide it, so it'll be 1/4 of what? But look at this. Amber, look what I'm leaving with the dx, the x cubed staying over here with this. All the x's are staying over on this right side. I just divided that little 4.
Yeah.
Substitution time. Let's rock and roll. Where are you coming? Shh. What's that? You. See, everything, all the x's have to go away. Well, what's replacing the x cubed and the dx? So look, so, all right, you're out, and I'm putting in place of it a 1/4 du. So, any suggestions about the 1/4? Now you got a clean integral. What's the integral of cos? Positive sine. Plus Charlie, because there are no numbers.
Mhm.
Emma, don't forget to resubstitute. What
So
was you?
Wherever there's you make it an x.
Oh, but look what we let you equal to in this problem.
Oh, x to the 4th.
There you go. 1/4 sine of, and I can check this, couldn't I?
Also, this is the same thing as the E, just, also, this is the simple harmonic motion, right?
You got it.
That's what they
What
call?
was the original question, problem?
Oh, evaluate the indefinite integral.
Of what?
And it was, I'll put it over here. The original one before I crossed everything out. Yeah, I'll put it right next to it. It was the integral of x cubed cosine of x to the 4th inside the parentheses dx.
D.
Okay? Josephine?
Do you ever get a power difference of more than one?
I'm not, well, so I can be careful. It's like, not on these, because what, you could tell what would happen. It wouldn't what? It wouldn't work, because this step we just differentiate, and by power well, it goes down by. But now, sometimes we get trig functions, okay? Some things don't deal with that. Trig functions, logarithmic functions. So before we leave today, we'll do some logs, right? But yeah, you're right. Now, are there other techniques out there? Yeah. One of the hardest, though, Josephine, was that flat out e to the x squared alone. Substitution rule doesn't work. You know, x squared versus just
Oh, so
nothing there. So
I mean-
mathematicians kind of went, what are we going to do with this? Now think about it. What can we fall back on? If it was a definite integral, we could go back to Riemann sums and set up like over the integral, and if like 1,000 rectangles underneath the curve, and we'd probably be accurate to about 8 decimal places or so. You know, that's what I mean with in terms of your career, where you're going to be like, oh, okay. I can approximate it to 8 decimal places. That's good enough for me. If there's no technique of it. All right. Taking it slow, Here you go. By the way, I keep writing 5-4. I'm sorry, this is 5-5. This is substitution rule. All right, this one's going to be interesting. Because it may look like product rule, but it's the reversal of it, of the chain rule. This is substitution rule.
So always take the one with the higher power, right? So it is
I know.
secant square x, right?
So I'm gonna hear you and I looking at this. Tan x times what? Secant squared of x. We don't know what to let u equal to, do you agree? But it's obvious this must involve, it's a good possibility this involves the substitution rule. You go, why? Because that's the only rule we've learned so far. Okay, yeah, but it's not just gonna be something alone. So when I've got this tan x times secant squared of x, and I'm trying to integrate this, I gotta let u equal to something. So how about you and I think about the trig functions and their derivatives. I'm gonna go way over here. I got the SCSES. And what's the derivative of tangent of x?
Secant square x dx.
Aha. This is gonna help us. Our knowledge of that. You go, why? What I'll do is,
Oh,
over
okay.
here, I'll let u equal the tangent of x. I'll let u equal the tangent of x. And you go, why am I doing this? You know? By the way, if you tried something and didn't work, you just try again. I'm gonna let u equal to tangent x because I have knowledge of trig derivatives. The derivative of tangent of x is secant squared of x. Do you follow me?
Mm-hmm.
So if I do this, what happens in step 2?
Du.
Who else emerges?
Du.
That other piece. Uh-huh. There we go. du equals secant squared x dx. Cool. Now, when this is the first time this is happening, Josephine, you asked about this earlier. I don't see a constant. Oh, it's a 1. So do I really have to go to step 3?
No.
No. This is the first time that's happened yet today, but you're like, I don't have to go to step 3, right? Because there's no what? 2 in front, or 3, or a 5. It's just an invisible what? 1. So when I do my 2 boxes to substitute, u and, well, this didn't have to occur, so I get to use that one. So sometimes you get this done in 2 steps, not always. I didn't go to step 3 because I didn't get this what? A 3 over here, or a 5. So I'm going to go right now. Here we go. What's u equal to? U becomes, so I'm going to take out the entire tangent of x and put what?
U.
U. Now what's this? I love this part. What's du remove?
Secant squared.
Everything else. I love it. You okay? Make it easier on us here. Bye-bye. Even that squared. Du. So let me write this again. Now the integral of x is x squared over 2. Bless you. So Arjun, what's the integral of u? It'll be u squared over 2. Oh, indefinite integral, no numbers, plus what? I look over it again. You're about to turn in your test. Does that look okay, or
No.
did I forget something?
Tan squared x over
The original problem had what letters? The original problem had the variable x in there, so I'm going to have to go back, and what did I let u equal to? Tan of x, so I'm going to have to write my answer like this. Now, can I show you how the back of the book likes to write this? Who in here likes to use this notation? They put the little square there. Do you like that?
Yes.
You could do that. Did you notice the textbook likes to do that? This, they like to write like this because it's less symbols. You don't have to though. You don't have to write it like that. That means this, but the textbook does this. They put the little 2 between the n and the what? Yeah, so how do they write this? You've seen it before. I know you've seen it before. We did it when we were doing derivatives. They write this as what? Yeah, they write it like that. Just a little bit easier, right? Less writing, but you don't have to. It means the same thing. So these.
So like tan squared x is like tan x times tan x, which is right.
That's right. Heck, you could write tan x times tan x over 2. Let's see. And you can start using trig identities if you wanted to. It would be sine squared over cosine squared.
Squared, yep.
With that 2 down there. Yep. Yeah. If you wanted to. Sometimes I'm about to mark something wrong and I see a student did a trig identity replacement for one of their answers. I'm like, oh, okay. He wanted to write the answer in sine and cosine. Okay. So that's what I mean. This is called an antiderivative. So there's other ways you can write antiderivatives because of the trig identities. Does that make sense? I mean, this problem alone, I think there's 3 ways I can think of you can write that answer. See, when there's options here. Josephine, like what would you let u equal to? There's different ways to do that problem.
Any of them.
U equals.
That would work.
I would
There's other options. You know why this works? Because what's the derivative of sine?
negative.
Cosine. But you could have used u equal to cosine because the derivative is a negative one. Sine. So it's funny that this would work. But I'm going to use your suggestion. So u equals sine of x, du equals cosine. No constant. Stop here. What's this replace?
Sine of x.
Du. What replaces the cosine x dx?
Du.
Du. What's the integral of u? Du.
Half u squared over 2.
U squared over 2. Plus Charlie, right?
Mm-hmm.
If you made u equal cosine, wouldn't you have to make the whole thing negative?
Yep. So it would give a different answer, wouldn't it? But I want to tell you, these antiderivatives, they'd be equivalent. You go why? Because of the plus c. So I would have to make an answer key, Josephine, for the different ways people wrote the answer. So what's one way to write this answer? U was what? plus Charlie,
Mhm.
plus Charlie, plus C, right? You could put the 2 right there if you like to do that. But obviously, if we used U equal cosine, this answer would have had a different but both are okay. There's different ways to write the antiderivatives. You know why? Because of the plus what? Plus C. That's why. But when it's definite integrals, no matter what, you're going to get the same definite answer. That's the beauty of mathematics. Cool? All right, try another one. We haven't seen any fractions yet. All right. I think I'll use 2. And when sometimes the author likes to use a y. Okay. I know. Might as well do it. Sometimes the author likes to use what letter? Y, or T, right? Okay. By the way, could you just start the problem and say y equals x and change them all to x's if you wanted to? Yeah, feel free to do all x's, that's okay. I bet you all know what to let u equal to. A lot of times it's the thing in the exponent, or a lot of times it's the thing in the parentheses. But when there's a power difference, it's the one with the higher power by 1. Well, this, I don't see like a power difference. But I see something in the parentheses. What do you think I let u equal to?
2y plus 1.
You nailed it. Okay. Composite function. du, now what's that derivative? 2, I gotta put dy, everyone, right?
Mhm.
2 dy. Now, Josephine, I will have to do step 3 because I got this 2 to pop up, huh? Or do I have to? I'm gonna do it, but watch, I'm gonna fall back. A lot of you are gonna tell me, hey, professor, you could have stopped at step 2. So I'm not out to confuse anybody, but Josephine, I'm gonna follow my what, step-by-step method. I see a constant, right? And I said this works every time. If I get a constant,